This is the Enterprise Intrigue track. We are in Palace 1. We are here to hear about CloneWise, automated package clone detection from Silvio Shazade. Did I get it right?
Close enough.
Okay.
Thanks for attending my talk. There's not many of you here, but I think there'll be some interesting things that I'll say. And the title of my talk today is Automatically Detecting Package Clones and Inferring Security Vulnerabilities from a tool that I've developed called CloneWise that is planned to be integrated into Debian infrastructure and hopefully help improve security for Linux. So just a little bit about who I am and where this talk actually comes from. I'm a PhD candidate at Deakin University in Melbourne, Australia. My research interests cover things like malware detection and automated vulnerability detection. The talk that I'm giving today covers automated vulnerability detection, but I also research other aspects of that, looking at static analysis of binaries, using decompilation data flow analysis and so forth. I'm also a book author. Software Similarity and Classification was published by Springer earlier in the year, and that covers and overlaps the malware detection research that I'm doing, looking at malware variant detection and so forth. I'm a Blackhat speaker from the past. I was last year in 2003. But I've also spoken at other conferences as well, including academic conferences, and I've published in academic journals and so forth. I've got a website, fucodeshoe.com. Has some free web services that do malware detection and software similarity. It also has some content on it and a wiki on software similarity and classification. So this talk is about embedded or cloned code. The word code clone, comes from academia where they do code clone detection. And code clone detection is detecting duplicated fragments of code, which has problems because it causes maintainability problems. In this particular talk, I'm talking about embedded or cloned packages. And what happens is that developers sometimes embed code from third-party sources. So they might statically link a library, for example, statically linking libpng. They might maintain an internal copy of a library. For example, libpng is copied in the Firefox source. Or sometimes developers fork a library. They make significant changes to the library, so they can't really use the system-wide shared library. There are lots of examples of embedded or cloned code. XML parsing, for instance, libxml, the expat XML parser, embedded in lots of stuff. Image processing has lots of libraries that are used and embedded elsewhere. We have libpng embedded in Firefox. There are also libraries like libtiff. There are JPEG and GIF libraries as well. Networking is a classic example is OpenSSL, which is embedded in lots of stuff. And compression, again, a classic example is zlib, which is embedded pretty much everywhere. Embedding code is generally a bad practice, and Linux policies generally disallow this. Debian, for instance, I don't know if you can read that, but it's part of their policy to say that embedding code from third parties is not a good idea, and that you should use a system-wide shared library. The reality is people still embed and bundle code, and what the problem eventuates into is that you have multiple versions of that package now existing. So libpng exists in at least two places now. It exists in the original package and in the Firefox sources where it replicates that libpng source. So each individual copy needs patches and manual patches every time there's a libpng bug or vulnerability. And what tends to happen in real life is that these embedded code copies become out of date and therefore fall insecure as more vulnerabilities are found against them. The manual approach to find embedded code is to use signatures, typically based on version strings. For example, in 2005, this was done on a mass scale for zlib. There was a vulnerability that appeared in zlib, a remote code execution vulnerability. And zlib is pretty much embedded in so many places that no one in Debian really had an idea of the extent of where zlib was embedded. So Debian created an antivirus signature based on the version string that identified zlib embedded in executable binaries. They did this against the entire Debian repository and found lots of cases where zlib was embedded and had those outstanding vulnerabilities. I've shown some other examples of version strings from things like bzip2, libtiff, and libpng. Most libraries will include a version string, so it is a good idea if you want to create a manual signature. The problem is there's so many packages in Linux. We're looking at 10 to 20,000 packages in a major distro, so it's really not practical that you can create a signature for every single package. And it's not like we're talking about just libpng or libtiff as the only embedded libraries that are used. Debian manually track 420 libraries, so it's quite significant. And Debian is one of the better distributions because most distros don't track this problem at all. It was only after we submitted information to Red Hat did they actually start creating a wiki to track embedded code copies like Debian. So we think that most vendors should do this, but at the moment Debian is really is really doing the best out of this. And that raises the question, of course, is that if people aren't tracking these things, how many vulnerabilities are there? Debian tracked them and there's still lots of vulnerabilities, so all the distros that don't track them, we're looking at lots of outstanding vulnerabilities. And how do we automate this process? And that is the focus of this work. The example I've shown in that image is from Debian's manual created database, which tracks embedded code copies. So we look in the example, I don't know if you can read it, but peercast in the bottom section is embedded in 2 packages, GNOME peercast, and in 2 different versions of that software as well. So the outline of this talk is that I'm going to give a problem definition, define exactly what I'm going to try to solve, and then describe the approach that I'm taking. The approach is based on machine learning and using statistical classification. So I'll be using that to classify packages as sharing or not sharing code. It's a good approach, I think, but it's quite slow, so we need to scale the analysis. And to do that, I've used an Amazon cluster and used multi-core and cluster computing to do that. Then once we've built a database of clones, which I have done, automatically or semi-automatically try to infer vulnerabilities and discover real vulnerabilities in software. I'll talk about the implementation and how to evaluate such a system using comparing our results that are automatically generated with Debian's manually tracked database. I'll discuss some general points, talk about related work, talk about some things that I intend to do in the future, and then conclude the presentation. So the problem definition is basically to find package code reuse in sources, source packages. This is a source level analysis, so I'm not looking at binaries. I'm not looking at static linking as well. There has to be replication of the code in the source tree. And then based on that, infer vulnerabilities that are caused by out-of-date code. So in the example that I've shown here, we have the Firefox source. libpng is roughly a subset of that, the sources, but it's not a perfect subset because some code in libpng isn't embedded in Firefox. But roughly, it's a good subset. The approach that I'm taking, that we're taking at Deakin University, is to consider the problem, the code reuse detection problem, as a binary classification problem. And that just means that we're asking the question, do packages A and B share code, yes or no? So it's 2 classes, a binary problem. To do that classification problem, to solve it, we need features to pass to our classifier. So the features that we're using are the number of common file names between 2 source packages, the number of identical hashes between 2 source packages, and the number of similar hashes between 2 source packages based on fuzzy hashing and fuzzy content. So the binary classification is comparing 2 packages, but what in fact we want is to know every package in the repository that embeds a particular library. So we take that library, package A, and we ask, does it share code with any other package in the repository? So we apply that binary classification problem to every package in the repository, and that gives us our answers where that library or package is embedded. So the solution is based on machine learning and statistical classification. But what exactly is the classification problem? Classification assigns classes to objects. So a good example is the spam detection problem. You have an object, which is an email. You have two classes, one of those classes being the email is spam, the other class being the email is not spam. And then you simply assign one of those classes to that object. So is the email spam or not spam? The major approaches to do classification are supervised learning and unsupervised learning. There are also other approaches such as semi-supervised learning and reinforcement learning, but the main approaches are supervised and unsupervised. In supervised learning, you train a classification model. So you give it labelled data where you have a set of objects with their known classes, and then you train that model, and then once it's fully trained, you're able to ask it, give it unknown objects, and it will tell you what class they belong to. In unsupervised learning, you don't have any labelled data. So the general approach to solve this is by using clustering. Clustering groups together similar items or similar objects, and these clusters identify classes, different classes. So in the spam problem, cluster analysis might identify that there's a class that roughly matches this email is a spam class, and another class which represents the email is not spam. To perform classification, you typically need features in a feature vector. So a feature vector is simply an array, an ordered list of elements. And in CloneWise, we've used 26 different types of features. Some of the features include the number of common file names between two packages, the number of file names in a package, and so forth. I'll talk a little bit more detail about each type of feature that we've used in the next set of slides. So the first major class of features that we're using is the number of common file names between two packages. So the example I've shown in that large table has some directory contents from the expat library, the expat package, and the TLA package. And what we can see is there are a lot of common file names between them. So we might have something like xml.toc.c, which is quite unique as a file name. Also, it's important to recognise the difference between source and data file names. We recognise source file names by the extension that they're using. So I've got a list of extensions that we recognise because sometimes it's probably more important to know that libpng.c is shared between two packages as opposed to a file name called readme. We also normalise the file names, so we convert the file names to lowercase. We remove punctuation characters from them, and so forth. Another type of feature that we're using is the number of similar file names. The previous slide talks about identical file names after normalization, but in this feature we're using the number of similar file names, again applied to source and data file names. One way we can determine similarity between file names is using the string edit distance, also known as the Levenstein distance. Using the edit distance, we can construct a similarity score. And if the similarity is greater than or equal to 85%, then we say that those two file names are similar to each other. We also look at the hashes and fuzzy hashes of the fuzzy hashes. We look at the content and determine their similarity using fuzzy hashing. So we use the program SSDeep to do this, which is based on piecewise, context-triggered piecewise hashing. We use three types of features: the number of identical hashes, which represents the content is equivalent, the same. We use the number of hashes where the similarity is greater than 80%, and the number of hashes that are greater than 0%. So basically we're looking for similar content. SSDeep, or context-triggered piecewise hashing, is good at identifying near duplicate blobs of data. It's not so good at detecting similarity between quite different types of data, but for near duplicate data, it's quite good. And I've shown an SSDeep hash below. The SSDeep hashes are compared using the string edit distance again, and that identifies the similarity between them. What we notice, though, is that, again, some files are more important than others. So libpng.c is probably more important than files like readme makefile, to do, etc. because libpng.c occurs very infrequently. Files like readme occur in almost every package. So what we do is we score the file names based on what's called the inverse document frequency. The inverse document frequency gives a weight or a score to a term based on how frequently that term occurs in a corpus. So the more frequent a file name appears, the less it's weighted. The less frequently it occurs, the more it's weighted. And we use a feature based on summing those weights or scores for the set of common file names or similar file names. When we look at comparing similar file names to each other, an issue occurs. One file name might match, one file name in one package might match more than one file name in another package. So which file name should we match to each other? What scores do we use? Well, each matching has a cost, and that's the score that I talked about in the previous slide based on the inverse document frequency. There are lots of matchings possible, so we choose a matching that maximises the sum of those costs. Now, this problem is actually known quite well in combinatorial optimisation as the assignment problem. The formal definition is given, but the informal definition is quite okay as well. We can solve this optimally in cubic time using the Monkrez or Hungarian algorithm, but in practice, even cubic time is quite slow when we're looking at a large number of files in a package. So in practice, we use this for files that do contain a lot of files. These packages that do contain a lot of files. It's also solved, optimally solved using a bipartite graph matching algorithm, which is the figure that I've shown there. Classification is all about features, but what we know is that some features are more important than others. Some features are redundant. Some features are so chaotic that if you include them in your feature vector, it actually reduces the accuracy of your classification algorithm. So there are a number of approaches that are used to remedy this problem. We can rank features based on assigning a score or a rank based on a metric to a feature, and then we can exclude those features that rank quite poorly. This is a type of subset selection, and there are different ways of performing subset selection. We can choose subsets of our features, pass them to a classification algorithm, and see if our accuracy improves as well. We chose not to use feature selection. We experimented with it, and in some cases it does improve accuracy. It's certainly possible that in the future we will include a more thorough feature selection algorithm, but the trade-off is that it takes quite a long time to run the subset selection. So we've got our binary classification problem, which is, do these two packages share code? We've extracted features from these packages, constructed a feature vector. Now we move on to the classification algorithm. If we consider the feature vectors as an n-dimensional point in space, we can possibly construct a plane, a hyperplane, that separates two classes, or two classes that those feature vectors represent. This is what's known as a linear classifier. There are also non-linear classifiers when we relax that hyperplane and make it a non-linear function, such as a parabola or a cubic function and so forth. Another type of classifier, which is interesting to note, are decision trees. And these basically are a set of decisions or rules that enable us to classify an object. Okay, so that's the basic solution that we've taken to classify whether two packages share code or one is embedded in another. The problem is it's really quite slow. We have to perform that classification algorithm to every package in our repository, and then we have to do that again for every single library that we're looking at. So we needed to scale the analysis. The first way I've done this is by using a multi-core system, speeding up clone detection on a single package. So remember that to identify when a particular package is embedded in the repository, we apply that classification problem to every package in our repository. So this can be done in parallel, of course, and that's what's known in parallel and distributed computing as an embarrassingly parallel problem, because we're looking at a number of non-connected components that we can break down our problem to. And we use the OpenMP compiler directives to implement this solution. I also use clustering using the OpenMPI API, which is the message passing interface. It's the most well-known cluster API that's available. There are things like Hadoop. Hadoop is newer, not as flexible as OpenMPI, but Hadoop has some advantages as well. There's Amazon infrastructure that we could have used, but it costs more as well. So the OpenMPI solution is actually cheaper for us when we're using web services. So again, a single job is clone detection on a package. The previous slide, I talked about improving the performance of detecting when one particular library is embedded in the repository. Clustering does the same thing, but in parallel across different libraries. And it's based on having a work queue, having each node as a slave and consuming jobs from that queue. Again, it's an embarrassingly parallel problem. We ran the analysis on a 4-node Amazon EC2 cluster. Each node had dual CPUs and 8 cores per CPU. That is 88 EC2 compute units, and they've got a metric of how to evaluate what an EC2 unit is. Each node in the cluster had 60.5 gig of memory. And we did this analysis not on every library or package in the repository, but those 420 tracked libraries that Debian has that manual database for, and this makes the time more feasible. Even with that, it took 4 hours on an Amazon cluster to determine those 420 libraries where they were embedded. We stored the results for later use, so we cached this so that we could use it later on and that Debian can use it as well. So we've got our clone database now. We have a database of when particular libraries are embedded elsewhere in the repository. We want to infer security vulnerabilities from that. So there are lots of standardization efforts that have been made over time. There's CVE, which everyone knows about, I'm sure. In a CVE summary, there's some useful information that we'll use a little later on, and I'll just describe this particular summary. It says an off-by-one error in the OP read rec function in readrec.c. For most open source software, in the summaries they'll include the actual file name that is vulnerable, which is useful, and we can use that later on, and I'll talk about that shortly. Another thing of interest is the Common Platform Enumeration, which is CPE, which is basically an attempt to come up with standardized names for software packages. Debian also do security tracking. They have a public subversion repository. And they track things like CPE. They associate CPE names to native Debian package names. They're the only vendor that I know that does this. We asked Red Hat if we gave them a list of automatically generated associations, if they would use it or if they would track it. They weren't that interested in it. But I think it's actually, I think Debian has the right idea, because what they do is when a new CVE is released, they look at their CPE mappings and they check what native package it refers to, and then they check their own CVE database and make sure that that vulnerability is being tracked. So again, what I just said, Debian tracks CVEs. For every CVE, they associate every package that is affected by that CVE, and we use that information to infer vulnerabilities. So this is an example of the tool and how it can be used. You basically, when you see a CVE appear, in this particular instance, it's a libpng vulnerability. You run the CloneWise tool to say where is libpng embedded in the repository. And libpng is embedded in IA32 libs. So every time there's a new libpng vulnerability, you run the tool and then you verify that those patches have been applied to those cases where libpng is embedded, or you verify that it's not affected by the libpng vulnerability. And you do this for every package that a CVE comes by. But that's a semi-automated approach. You know, it's useful, but we really want a fully automated approach. So one way of doing this is sort of what I talked about before, but just formalising it a little bit. We take a CVE, a new CVE that appears, we match the CPE name to the Debian package, we pass the CVE summary and extract the vulnerable file name, then we find clones of that package that contain that file name. We trim the results so that we ignore packages that use the dynamically linked library, and we check Debian's CVE database to see if this vulnerability is being tracked. And if it's not being tracked, we report it. An example of this, a libpng vulnerability again. We run the tool, clonewise find bugs, giving the CVE name, and it tells us that libpng is cloned in IA32 libs, it's unfixed, and it's affected by this particular CVE. It also automatically tells us that it's a libpng vulnerability from that CVE, and that the file name in question is png-rutil.c. So this is, I think, an outstanding vulnerability. It's an old one, so it's probably something's gone askew, but there are lots of vulnerabilities that can be found like this. So that's basically the tool. It can find vulnerabilities, it can find clones, and I'll talk about the implementation and how we evaluate in the next section. So it's about 3,500 lines of C++ code and some shell scripts. I think it's quite small for the functionality that it performs. It's an open source project, it's on GitHub. Debian Linux plan to integrate this into their own infrastructure so that they're automatically finding clones and fixing vulnerabilities. So, yeah, that's the implementation. The next part is how we evaluate this system. So the first thing that I'm looking at is using a file name a good feature? You know, how common are file names in packages? Does every package have unique file names, or do they use the same file names? So I took Ubuntu Linux. It has about 3 million unique file names in the source tree. And interestingly enough, the frequency of those file names occurring follows an inverse power law distribution, which is shown below. Not the theoretical inverse power law distribution is shown below. The R-square value of regression analysis, which describes how closely our data actually matches those theoretical curves, is quite high at 0.92. So it says that it follows that curve very well. To move on to evaluating the system in a more thorough way, we needed to establish a ground truth. We needed some data to compare our system to. So we took Debian's manually created database, and we parsed this. It's called embedded code copies.txt. It's in the Debian security tracker. You can download it. It's not really machine readable, but it's good enough that we can use it. We cull entries that we can't match to packages. A lot of the times they're using non-standard names, or so the naming convention isn't perfect, and I think this needs to improve over time. But we extracted about 761 cases of package A is embedded in package B. So those are our labelled positive cases. We also needed negative cases where package A does not share code with package B. And to do that, we basically took 2 random packages from the distro, and if they're not in our positive list, we label them as negative. We took about 50,000 generated labelled negatives. Some of this data is unclean. Some of those cases, they're actually going to be positives. But this is reasonable enough to compare our system with. Our system identified 34 previously unknown clones in Debian, and I think there's lots more. So it's still a work in progress. We'll improve it over time. We evaluated 4 classification algorithms. We actually evaluated many more, but these are the ones we're going to talk about. The random forest classification algorithm gave the best accuracy. And we also noticed that some of these algorithms have a decision threshold, which is basically like saying how probable, how much certainty exists in the classification output. And so increasing that decision threshold reduces false positives. It also reduces true positives, but we accept that because we really want a system with a low false positive rate to make it practical. So in our system, we predict about 3 false positives in 10,000 classifications, and that's probably an upper limit. our data isn't clean, there are going to be positive cases in the negative label data that we generated. So 3 in 10,000 is probably an upper limit. So the 4 classification algorithms that we tried were the naive Bayes classifier, a multi-layer perceptron, which is an artificial neural network. It's also a non-linear classifier, the C4.5 decision tree, and the random forest classifier as well. And you can see from our results, with the random forest algorithm, we got about 70% a true positive rate, and a 0.11% false positive rate. So that's less than 1%. But we think that it's still, the false positive rate is still too high. So we increased the decision threshold to 0.8 in the random forest, and we reduced our accuracy, our true positive rate, to 58.61%, but we decreased our false positive rate to 0.03%. So at this point, we're starting to think that it's going to be, well, it is a practical tool, and it's not going to bog down an analyst who's using the tool. Our clone detection took about 4 hours to run on the Amazon cluster that I talked about, and that's scanning about 420 libraries. So we really need a much bigger cluster to scan the entire repository. Hopefully we'll get this in the future. Something interesting that we noted was that the MPI scatter function in OpenMPI to do static job assignment to our slave nodes worked out really badly, because what happened is that some nodes completed their jobs really quickly and some nodes had no jobs at all. So we really didn't utilise the cluster very well. So we re-implemented that using work queues, which I talked about earlier, and our performance improved quite considerably. We also needed to use multi-core. It wasn't just, an optional thing. Again, because we had starvation and whatnot, some jobs would take a very long time to run, and multi-core would have made that load much more balanced. So these are the vulnerabilities that we detected. We also detected some other ones, but I'm still working through the results. So still a work in progress. It's around 34, I think, vulnerabilities in Debian and Fedora. They're all low-key vulnerabilities. The most interesting one, I think, was security-enhanced Postgres SQL, which was actually a fork of Postgres SQL, but a beta version of that. So, in fact, when they released an advisory, when they released a vulnerability against this beta version, they sort of ignored the fact that it was being used elsewhere. So we first started giving Debian reports of clones and vulnerabilities, and what they did was give us write access to their security tracker so we could enter this data ourselves and help. And I think that's worked out really well. Red Hat created a wiki that now tracks embedded code copies. I use the term embedded code copies because remember from that previous slide, Debian has a file embedded code copies.txt. That's their terminology, so I've sort of mixed it up with the academic clone code and Debian's embedded code copies terminology. Debian planned to integrate CloneWise into infrastructure, which is really good, so they want to give us a subdomain as well, and so we can have a public online tool where you can find clones and whatnot. Now, it's an interesting problem that CVEs don't actually reference CVEs of embedded libraries. So if Firefox has a libpng vulnerability, it won't reference the libpng CVE directly. Red Hat will do this, but most vendors don't. So it would be really nice if CVE natively supported this ability. It would really be useful and help automated vulnerability detection. Another issue that is of point is that CloneWise detects code reuse, but it doesn't strictly detect if one library is embedded in another, it just detects that they reuse code. So if zlib is embedded in packages X and Y, then CloneWise will detect relationships between all three of them. What we really want to know is X is not cloned in Y, but zlib is cloned in X and Y. And the way we can mitigate against this is by performing clone detection on the libraries that we know are of interest. So that's what we've started with. I think future work will work on refining those results a little more. There's some related work. This isn't in isolation. Debian have performed an audit of zlib back in 2005. Also, there are things like plagiarism detection, detecting reuse of code in source code. And there are different approaches for that, using things like attribute counting, counting the number of times particular features occur, or structure-based system, which basically look at representing programs in some structured way and comparing those structures. So classic attribute counting systems or Halstead complexity measures. There's also in the academic world code clone detection. So we can do things like tokenize source code and compare those sequences. Or we can look at the abstract syntax trees of a program and look at maximum common subtrees or subtree, tree isomorphism and so forth. In the future, I think I'd like to look at things like SourceForge and GitHub. Instead of just analysing Debian Linux or Ubuntu Linux or Fedora, analyse a huge public repository of source code and see what results we get. I could also try other operating systems, such as the BSD-based operating systems and so forth. It would be nice to integrate this system into a build or packaging system so that when you go to build your Debian package or your distro-specific package, it will warn you and say zlib is embedded, it might be vulnerable. And again, the immediate future work is to integrate this into Debian Linux's infrastructure. So that's pretty much the talk. That's the tool, that's the implementation and the evaluation. I've got a website that I talked about earlier that has more than just this particular tool. I've got another free web service called Simcia, and it's a free flow graph-based malware similarity service and builds things like evolutionary trees to show malware relationships and families. It's a large code base, and I'm happy to talk to anyone about it. In conclusion, Linux vendors have a huge number of packages in their distros. We're looking at 10 to 20,000 of them, and most of them don't track this type of stuff. Only a couple do, and only one that does it actually reasonably well. So how do we audit these massive systems for this type of problem? The tool that I've talked about today can provide a solution to this and help improve security. So if you want more information, go to my website and I'll take any questions.
So you said that you had some features that just threw things off. Can you tell us more about that?
So the question was that I talked about features that I use to perform classification, and I also talked about feature selection, that some features throw off the classifier. So to explain a little bit more about that specifically to CloneWise. So one particular issue that we had was that when we include the file name, the number of file names in each package as a feature, from our label data, we say package A is embedded in package B. Now, package B, if you include the number of file names as a feature, because we do, it actually decreases the accuracy of the system. But I haven't really wanted to exclude it and talk about it because it's sort of an ad hoc method that I just tried removing random features and saying, well, I'll see if this improves anything. So the better way of doing it is by using a subset selection algorithm that will automatically determine which features to remove. But it takes so long on our data set that I haven't really been willing to sacrifice a week to run the tool, to run this algorithm. In the future, I think we will do that. But at this point in time, I don't really want to go down that path and talk about it as I just did. So, okay.
Thank you, everybody.